Imagine for a moment that you're standing under a clear night sky, far from city lights, gazing up at that ancient tapestry of stars. For thousands of years, humans have looked up at that very same sky and tried to make sense of it all, to understand the shape and structure of the cosmos itself. We've gone from believing in a flat Earth under a heavenly dome to mapping out an expanding universe that might be flat, spherical, or even shaped like a donut. But what if this whole time we've been missing something profound? What if the shape of the universe isn't just a little different from what we thought, but something so strange, so unexpected, that it forces us to rewrite the story of reality? This isn't just some abstract puzzle for physicists to debate in lecture halls. If the geometry of the universe isn't what our textbooks claim, it changes everything. It reshapes our understanding of time, space, and our own place in the cosmos. It could mean that dark energy and dark matter, those mysterious forces we can't see or touch, are nothing more than illusions created by a geometry we haven't yet recognized. It might mean the universe is finite yet without edges, or that if you traveled far enough in one direction, you'd eventually return to where you started. These aren't wild fantasies, they're real possibilities grounded in the latest research and the deepest questions science is asking today. In this video, we're going to explore why the shape of the universe matters more than you might think. We'll journey from the earliest models of the cosmos to the cutting-edge theories that are challenging everything we thought we knew. We'll look at the anomalies in the cosmic microwave background, the puzzling discrepancies in how fast the universe is expanding, and the large-scale structures that seem to hint at a curvature we can't quite measure yet. This is more than astronomy. It's a detective story spanning the history of human curiosity, and it invites you to see the universe in a whole new light. So settle in, open your mind, and get ready to question the very fabric of existence, because by the end of this, nothing may look the same. Long before telescopes and satellites, our ancestors looked up at the heavens and tried to map the cosmos with the tools they had: their eyes, their intuition, and their myths. In ancient Mesopotamia, the universe was often envisioned as a flat Earth floating in a vast sea, sheltered by a solid dome arching overhead, a celestial vault punctuated by tiny holes letting through the light of the stars. The Egyptians saw a star-studded goddess, Nut, arched over the earth, her body creating the sky. These early models weren't just primitive guesses, they were coherent systems built on observable reality. If you stand in an open field, the world does look flat, and the sky does appear to curve down to meet the horizon. Their cosmic cartography made sense for the world they could see, but it was limited by a perspective anchored firmly to the ground. Then came the Greeks, who introduced geometry and reason into the mix. Philosophers like Aristotle argued for a spherical Earth based on the curved shadow it cast on the moon during an eclipse. But it was Ptolemy in the 2nd century who created a model that would dominate Western thought for over 1,000 years. A geocentric universe where the Earth sat motionless at the center, surrounded by a series of perfect, transparent spheres that carried the moon, the sun, the planets, and finally the fixed stars. This system was mathematically sophisticated. It could predict planetary motions with remarkable accuracy, but it was also incredibly complex, requiring planets to move in tiny circles called epicycles as they orbited. This model reflected not just scientific thinking, but a philosophical and religious view of an ordered, Earth-centered cosmos, a universe designed around humanity. Everything changed in the 16th century when Nicolaus Copernicus proposed a heliocentric model, placing the sun at the center. This was more than just swapping one center for another. It was a radical shift in perspective that dethroned Earth from its privileged position. Johannes Kepler later refined this with his laws of planetary motion, showing that planets move in ellipses, not perfect circles. Then Galileo's telescope revealed moons orbiting Jupiter and imperfections on the Sun, shattering the idea of perfect celestial spheres. But even with these breakthroughs, the universe was still seen as a static, finite container, a vast stage with a fixed set of actors, its overall shape still undefined and largely unexplored. The real turning point arrived in the early 20th century with Albert Einstein's theory of general relativity. For the first time, we had a mathematical framework that didn't just describe objects moving through space, but described space itself as a dynamic, malleable fabric. Einstein's equations showed that matter and energy tell spacetime how to curve, and that curved spacetime tells matter how to move. This opened the door to imagining the universe not as a container, but as a physical entity with a shape that could be measured. Scientists realized the cosmos could, on the largest scales, be flat like an infinite sheet of paper, or closed like the surface of a sphere, curving back on itself, or open like a saddle, stretching away forever. The fate of the entire universe, whether it would expand forever or eventually collapse, was tied directly to this geometry of space. Each of these historical models, from the flat Earth under a dome to Einstein's curved spacetime, was shaped by the limitations and biases of its time. The ancients were limited by what they could see with the naked eye. The medieval astronomers were constrained by religious doctrine and a preference for perfect circles. Even Einstein's groundbreaking work carried its own assumptions, the idea of a smooth, continuous fabric of space, for instance. This historical journey shows us that every era's cosmic map was considered the final word until it wasn't. They were all provisional, shaped by the technology and philosophies of their day. And that begs a profound question. What if our current model, the nearly flat universe supported by modern cosmology, is also just a reflection of our own limitations? What if, in another 100 years, our descendants will look back at our certainty and smile, knowing we were missing something extraordinary? So where does that leave us today? The current leading model in cosmology is known as lambda CDM, or the lambda cold dark matter model. It's our best, most comprehensive attempt to describe the universe's composition, evolution, and crucially, its geometry. And according to this model, the universe is flat, not flat like a piece of paper in the everyday sense, but geometrically flat on the largest scales. This means that two parallel beams of light sent traveling across the cosmos would remain perfectly parallel forever, never converging or diverging. This flatness is intimately tied to a specific critical density of matter and energy in the universe. If the density were any higher, the gravitational pull would cause space to curve positively, like a sphere, eventually collapsing back on itself. If it were any lower, space would curve negatively, like a saddle, expanding into an ever-thinning emptiness. The fact that we observe a universe so perfectly balanced on this knife edge is one of the most profound mysteries in all of science. This conclusion isn't just a wild guess. It's primarily drawn from incredibly precise observations of the cosmic microwave background, that faint afterglow of the Big Bang. Satellite missions like Planck have mapped this ancient light in exquisite detail, and the patterns of hot and cold spots they found are a perfect match for what a flat universe would produce. The sizes of these fluctuations, the statistical distribution of them, it all points toward a geometry with zero curvature. It's a powerful, compelling argument that has convinced the majority of the cosmological community. This flat model gives us a tidy, seemingly complete picture, a universe that began with a big bang, went through a period of incredibly rapid inflation that stretched it flat, and is now dominated by dark energy, causing its expansion to accelerate forever into a cold, dark future. But here's the catch, and it's a massive one. This entire elegant framework rests on the existence of two entities that we have never directly seen or conclusively identified: dark matter and dark energy. Think of them as the invisible scaffolding holding up the entire model. Dark matter is the mysterious, unseen mass that provides the extra gravity needed to explain how galaxies spin and how large-scale structures form. Without it, galaxies would fly apart. Dark energy is the even more enigmatic force responsible for the accelerating expansion of the universe. Together, these two unknown components make up about 95% of the total content of the cosmos. Everything we can see, all the stars, planets, and galaxies, comprises a mere 5%. So when we say the universe is flat, we are essentially saying that the combined effects of this 5% of normal matter, plus 27% dark matter, plus 68% dark energy, all add up to exactly the critical density needed for flatness. It's a precise mathematical balancing act achieved by things we don't understand. This raises a fascinating and crucial question. Are dark matter and dark energy real physical substances, or are they ingenious mathematical placeholders? Could they be the modern equivalent of Ptolemy's epicycles, a complex fix we've invented to preserve a model that is fundamentally incomplete? What if the universe isn't flat at all, but appears that way because our interpretation of the data is skewed by a misunderstanding of gravity or the true geometry of space? The Lambda CDM model is a masterpiece of scientific inference, but it is built on a foundation of inferences, not direct detections. This leaves a tantalizing door wide open for alternatives, for the possibility that the universe's true shape is something far more strange and wonderful than a simple, flat, infinite plane. So we arrive at the first great cosmic mystery, a puzzle so profound it challenges the very foundation of our flat universe model. It's called the Flatness Problem, and it asks a deceptively simple question: why is the universe so exquisitely, perfectly balanced? To understand just how strange this is, think of trying to balance a pencil perfectly on its point. The slightest breath of air, the tiniest vibration, and it topples over. Now imagine balancing that pencil not for a second, but for over 13 billion years. That's the level of precision we're talking about with the universe's density. The fate of the entire cosmos is determined by its density, a value cosmologists call omega. If omega equals 1, the universe is flat and will expand forever, though at an ever-slowing rate. If omega is greater than 1, the universe is closed and will eventually collapse back in a big crunch. If it's less than 1, the universe is open and will expand into infinite thinness. The incredible thing is that for our universe to look the way it does today, filled with galaxies and capable of supporting life, omega must have been almost exactly 1 at the moment of the Big Bang. Not 0.99, not 1.01, but 1 to within 1 part in 10 to the power of 60. That's a 1 followed by 60 zeros. It's a level of fine-tuning so absurdly precise that it seems impossible to attribute to mere chance. If the density had been even a fraction different in those first moments, the universe would have either ripped itself apart too quickly for anything to form or collapsed back on itself long before stars and planets could ever appear. This is where the theory of cosmic inflation comes in, proposed in the 1980s by physicists like Alan Guth. It suggests that a fraction of a second after the Big Bang, the universe underwent a period of hyper-fast exponential expansion, inflating by an enormous factor in an incredibly short time. Think of it like taking a tiny, wrinkled crinkle in a sheet of paper and stretching it out over the surface of an entire continent. Any local curvature becomes so vast and spread out that it appears perfectly flat to anyone standing on it. Inflation, in effect, acts as a cosmic iron, smoothing out any wrinkles in spacetime and driving the density toward that critical value of 1, effectively solving the flatness problem by making it a natural outcome of this violent expansion. But here's the twist: while inflation is a leading theory, it remains just that, a theory. We have strong circumstantial evidence supporting it, but we lack direct smoking gun proof. Furthermore, inflation itself introduces new questions. What triggered this inflationary epoch? What stopped it? Some models even suggest that inflation could be eternal, creating a multiverse, a vast frothing ocean of bubble universes, each with its own random properties and laws of physics. In this staggering scenario, we simply find ourselves in one of the rare bubbles where the density happened to be just right for galaxies and life to form. Our perfect balance isn't a law of nature, it's a cosmic coincidence, a lucky draw in an infinite multiversal lottery. Other ideas, like cyclic models, propose a different solution entirely. Perhaps the universe has no beginning and no end, but instead goes through an endless series of big bangs and big crunches. In each cycle, the physics of the collapse and rebirth could naturally drive the geometry toward flatness, like a ball bearing finding the bottom of a bowl after being shaken. The flatness problem, therefore, isn't just a minor technical issue for cosmologists to solve. It is a fundamental clue that our geometric assumptions might be oversimplified, a glaring signpost urging us to look beyond our standard narrative and consider possibilities that are far stranger and more wonderful. But if the cosmic microwave background is the ultimate proof of a flat and uniform universe, then why does it contain such bizarre and unexplained fingerprints? This ancient light, a snapshot of the universe when it was just 380,000 years old, is not perfectly smooth. It's mottled with tiny temperature variations, and while most of these fluctuations fit the flat model perfectly, a handful of them stick out like sore thumbs. They are the anomalies, the cosmic glitches that keep cosmologists awake at night. The most famous of these is the so-called cold spot, a region of space that is significantly cooler than the surrounding areas. In a truly infinite and random universe, a fluctuation that large and that cold is staggeringly unlikely, a 1 in 50 chance at best. It's like rolling a die and getting the same number 100 times in a row. It's not impossible, but it strongly suggests the dice might be loaded. One compelling explanation is that this cold spot isn't a statistical fluke at all, but a window into the universe's true topology. Imagine space isn't an infinite flat plane, but a finite, multiply-connected shape like a torus, the surface of a donut. In such a universe, if you travel far enough in a straight line, you wouldn't just go on forever. You'd eventually loop back to where you started. Now, picture a massive void, a truly enormous region of space with far fewer galaxies and less matter than average. In a simply connected, flat universe, we'd see that void once, but in a toroidal universe, the light from that same void could, in theory, take multiple paths to reach us. It could come to us directly, but it could also wrap all the way around the universe and hit us from the opposite direction. The cold spot could be the ghostly echo of a single giant void, its faint signal amplified because we are seeing it twice, superimposed on itself. This would create a localized patch of cooler temperature that defies standard explanation, a cosmic double exposure etched into the oldest light we can see. The anomalies don't stop there. The CMB also exhibits a puzzling lopsidedness, an asymmetry often called the axis of evil by researchers. the temperature fluctuations in one half of the sky are statistically different from those in the other half. In a standard, infinite, and isotropic universe, the cosmos should look roughly the same in every direction. This pronounced asymmetry is like drawing a line through the sky and finding that the laws of physics seem to work differently on either side of it. Another strange feature is a curious lack of correlation on the very largest scales. The universe seems almost too uniform, as if the vast, distant patches of space are somehow out of sync with each other, violating what we'd expect from a cosmos that had enough time to even out its temperature after the Big Bang. These aren't just minor data points, they are fundamental challenges to the simplest version of our story. If the universe were truly flat, infinite, and simply connected, these patterns should not exist. Their presence suggests that our map of the cosmos might have hidden folds, twists, or boundaries we haven't accounted for. We might be like early explorers trying to chart the Earth while stubbornly insisting it is flat, misinterpreting every coastline as an edge of the world instead of a curve in a globe. The light from the CMB has been traveling for over 13 billion years to reach us, and along its unimaginably long journey, the very shape of the universe may have imprinted itself upon that light in ways we are only beginning to decipher. These anomalies are the cryptic clues, the subtle signatures of a cosmic architecture far more complex and wondrous than a simple, blank, endless sheet. Now, if the universe's geometry is throwing off our reading of its ancient light, it might also be warping our perception of its present-day behavior. This brings us to one of the most heated debates in modern cosmology, the Hubble Tension. At its heart, it's a story about two different ways of measuring the same thing, and they stubbornly refuse to agree. The thing they're measuring is the Hubble constant, a deceptively simple number that tells us how fast the universe is expanding right now. It's the current expansion rate, a single value that should be a cornerstone of our cosmic model. Yet, when two of our most trusted methods are used, they return two different, irreconcilable answers. It's as if you used two different rulers to measure the same table and got two different lengths. Something fundamental is clearly wrong with our tools or our assumptions. The first method acts as a local cosmic speedometer. Astronomers look at relatively nearby galaxies, specifically those with Type 1a supernova. These stellar explosions are what scientists call standard candles. We know their true, intrinsic brightness. By measuring how dim they appear from Earth, we can calculate their distance with incredible precision. Then, by measuring how much the light from their host galaxy is stretched or redshifted, we can see how fast they are moving away from us. Plot distance against velocity, and the slope of that line gives you the Hubble constant. This local measurement, refined over decades, gives us a very specific number, roughly 73 kilometers per second per megaparsec. This means that for every megaparsec, a distance of about 3.3 million light-years a galaxy is from us, it moves away 73 kilometers per second faster. The second method takes a completely different approach, using the cosmic microwave background as a sort of fossilized blueprint of the infant universe. Satellite missions like Planck have mapped the CMB's subtle fluctuations in exquisite detail. By feeding this detailed map into our standard model of cosmology, the lambda CDM model that includes dark matter and dark energy, we can run the cosmic film backwards to see how the universe evolved from that initial state to what it is today. This model predicts what the Hubble constant should be now, and this method gives a different, lower number, around 67 kilometers per second per megaparsec. The difference might seem small, but the precision of these measurements makes the gap statistically enormous. These aren't fuzzy numbers, they are both rock solid in their own domains, and they are unequivocally in conflict. This isn't just a minor academic disagreement. This tension suggests a crack in the very foundation of our understanding. If our standard cosmological model is correct, these two numbers should align perfectly. The fact that they don't means that the model might be missing a crucial ingredient, or that one of our fundamental assumptions about the universe is flawed. And this is where the shape of the universe comes roaring back into the picture. Our entire interpretation of both sets of data, from the local supernova and the ancient CMB, is built on the assumption that the universe is geometrically flat. Every distance calculation, every interpretation of redshift, every model of expansion relies on this foundational premise. Consider what might happen if that premise is wrong. Imagine for a moment that the universe has a very slight positive curvature, like a gigantic but faint sphere. This curvature would act like a cosmic lens, subtly bending the paths of light over immense distances. If we assume space is flat when it's actually curved, our distance measurements to faraway objects would be systematically off. A supernova we think is a certain distance away might actually be closer or farther, which would directly throw off our calculation of the expansion rate. Similarly, that same curvature would have imprinted itself on the pattern of the cosmic microwave background in a way we might have misinterpreted. Our models, stubbornly insisting on flatness, would have to contort themselves to fit the data, potentially creating the illusion of a discrepancy in the Hubble constant where none actually exists. The tension, therefore, might not be a problem with the expansion rate itself, but a colossal error in our cosmic cartography. Alternatively, this could point to something even stranger about the dark energy that's driving the universe's accelerating expansion. Perhaps dark energy isn't a constant force as we've assumed, but a force that evolves over time. Its strength could have changed between the early universe imprinted in the CMB and the more recent universe we see with supernova. Or the geometry of the universe might be influencing how dark energy manifests on different scales. We are forced to confront a truly mind-bending possibility that the laws of physics themselves might not be uniform throughout the cosmos. The Hubble tension is far more than a technical dispute over a number. It is a direct challenge, forcing us to question the very geometry of our reality and whether we are reading the cosmos's deepest rhythms correctly. If the universe's expansion rate seems to be sending us mixed signals, the very architecture of the cosmos might be offering its own cryptic testimony. When we zoom out to the grandest scales, the universe presents a principle known as the cosmological principle, which states that, on average, the cosmos should look roughly the same in every direction and from every location. It should be homogeneous and isotropic, a vast, featureless soup of galaxies with no preferred center or special direction. This idea of large-scale uniformity is a foundational pillar for our flat universe model. But what happens when we actually map the cosmos in 3 dimensions and find structures so enormous they seem to defy this very principle? These aren't just clusters of galaxies. These are cosmic continents, vast walls and filaments of matter that stretch across billions of light years, making our local supercluster look like a mere neighborhood. The most famous and challenging of these is the Hercules Corona Borealis Great Wall. Discovered by mapping the locations of gamma-ray bursts, the most violent explosions in the universe, which serve as brilliant beacons for distant galaxies. This structure is a mind-numbing colossus. It spans approximately 10 billion light-years in its longest dimension. To put that incomprehensible scale into perspective, the entire observable universe is about 93 billion light-years across. This one single structure, a gravitationally bound chain of galaxy clusters, takes up more than 10% of the observable cosmos. According to our standard models of cosmic evolution, there simply hasn't been enough time since the Big Bang for such an enormous structure to form through gravity alone. It's like finding a single mountain range that stretches across an entire continent. the forces required to build it are beyond what we thought possible. This is where the shape of the universe re-enters the conversation in a profound way. Our expectation of homogeneity and our surprise at these giant structures is predicated on the assumption of a flat, infinite universe. In such a cosmos, matter should be distributed in a largely random, statistically even manner on the very largest scales. But if the universe is not flat, if it possesses a global curvature, that curvature would act as a guiding hand, influencing how gravity pulls matter together over billions of years. A positively curved spherical universe, for instance, is a finite space. In a finite volume, there are natural harmonics, preferred scales, and modes where matter can cluster. It would be like the vibrations on a drumhead. Certain patterns and resonances are naturally favored. In such a cosmos, the formation of a gigantic, coherent structure like the Hercules Corona Borealis Great Wall might not be a statistical impossibility, but a natural consequence of the universe's geometry. The curvature itself could provide the scaffolding for matter to assemble on scales that seem impossible in an infinite, flat space. Furthermore, a multiply-connected topology, like a toroidal universe, could create the illusion of a giant structure where none actually exists. If space is wrapped around on itself, the same cluster of galaxies could appear to us in multiple places along different lines of sight. Our telescopes might see what we interpret as two separate giant walls at different distances, when in reality, we are seeing two different images of the same single structure. We'd be cosmic cartographers mistakenly plotting the same mountain range twice on a map because we didn't realize our world was round. The apparent violation of homogeneity wouldn't be a violation at all, but a simple error in our interpretation, a misreading caused by our stubborn insistence on a flat, simply connected model. So these vast cosmic formations are more than just curiosities. They are potential Rosetta Stones for deciphering the true geometry of the universe. Their very existence, their scale, and their alignment could be whispering secrets about curvature and topology that we've been deaf to because our models have always assumed a flat, infinite backdrop. By meticulously studying the distribution of galaxies and the subtle patterns in the large-scale structure, we might begin to see the signature of a global shape, a faint imprint of a cosmos that is finite, curved, and woven into a far more intricate and interconnected tapestry than we ever imagined. And just as the grand structures of the cosmos might be hinting at a hidden geometry, the very paths of light itself are telling a similar, and perhaps even more bizarre story. This brings us to one of the most powerful tools in the cosmologist's toolkit, gravitational lensing. Predicted by Einstein's general relativity, it's the phenomenon where a massive object like a galaxy or a cluster of galaxies acts as a cosmic lens, warping the fabric of spacetime around it and bending the path of any light that passes by. This allows us to see magnified, distorted, or even multiple images of distant galaxies lying behind the lens. It's a spectacular effect, and by carefully measuring how much the light is bent, astronomers can essentially weigh the lensing object. This has been our primary method for mapping the distribution of dark matter throughout the universe, as the amount of bending often reveals far more gravity than can be accounted for by the visible stars and gas alone. But sometimes the universe throws us a curveball. On occasion, we observe lensing effects that are simply too strong or too distorted, or arranged in a pattern that our standard models just can't explain, even when we add in the required amount of dark matter. The light is bending in ways that defy our predictions. These are the gravitational lensing anomalies, and they present a fascinating puzzle. Our immediate reaction is to assume there must be even more unseen mass there, more dark matter clumped in a way we didn't expect. But what if we're solving the puzzle the wrong way? What if the extra bending isn't caused by extra mass, but by the overall shape of the universe itself? Think of it like this. Imagine you're trying to navigate a vast, open plain you believe to be perfectly flat. You watch a distant traveler walk a path that seems to arc slightly for no reason. You might assume there's a hidden valley or a hill just over the horizon that you can't see, pulling them off course. That's our dark matter. But now, imagine the reason for the arcing path isn't a local feature at all, but the fact that the entire plane is actually curved. The traveler is simply following the intrinsic global curvature of the land itself. In cosmology, a universe with a global curvature, positive or negative, would naturally warp the paths of light rays on the largest scales. A topological defect, a kind of permanent kink in the fabric of spacetime left over from the universe's earliest moments, could act as a permanent lens, bending light in a consistent, predictable way that we've been misinterpreting as a clump of dark matter. This possibility turns a fundamental pillar of modern astronomy on its head. A significant portion of what we've mapped as the dark matter halo of a galaxy, or the dark web connecting galaxy clusters, might not be matter at all. It could be a geometric illusion, a phantom mass conjured by our misunderstanding of cosmic geometry. We've been meticulously charting the shadows, believing them to be solid objects, when in reality we might just be seeing how the stage itself is warped. Every time we add another dollop of dark matter to our models to explain an anomalous lensing observation, we might be inadvertently patching over a deeper truth about the shape of spacetime. The light isn't lying, we are simply misreading its testimony because we are using the wrong map to interpret its journey. So where does this leave us if we begin to question the flat universe model that has been our guide for decades? It opens the door to a breathtaking menagerie of other possibilities, each with its own profound implications for the origin, structure, and ultimate fate of everything. The first and most classic alternatives are the closed and open universe models, which are just as rooted in Einstein's equations as the flat one. A closed universe would be positively curved, much like the surface of a sphere but in 3 dimensions. In this geometry, the universe would be finite yet have no edge. If you could point a starship in one direction and travel in a perfectly straight line, you would eventually circumnavigate the entire cosmos and return to your starting point from the opposite direction, much like an astronaut orbiting the Earth. But this beautiful, finite package comes with a dramatic conclusion, the big crunch. The collective gravitational pull of all the matter in this closed cosmos would eventually overcome the outward momentum of the Big Bang, causing the entire universe to slow its expansion, stop, and then catastrophically collapse back in on itself in a fiery reverse of its creation. It's a cyclical story of birth, death, and potentially rebirth, offering a kind of cosmic symmetry that a forever expanding flat universe lacks. On the opposite end of the spectrum lies the open universe, a model with negative curvature, often visualized as an infinite, saddle-shaped surface. In this vast and lonely cosmos, parallel lines would gradually diverge, and the geometry itself would ensure that the expansion never stops. The gravitational pull of matter is too weak to ever rein in the expansion, leading to a fate sometimes called the Big Freeze or heat death. The universe would expand forever, with galaxies flying apart into an ever-cooling, ever-darkening emptiness. Stars would eventually burn out, black holes would evaporate, and matter itself might decay into a thin, featureless haze of particles spread across an infinite void. It's a stark, eternal, and ultimately silent ending, a universe that simply fades away into nothingness over trillions upon trillions of years. But why stop at spheres and saddles? The mathematics of topology invites us to consider shapes that are far more exotic and mind-bending. What if the universe isn't just curved, but woven into a complex, connected form? Imagine a three-dimensional torus, the volumetric equivalent of a donut surface. In a toroidal universe, space is finite, but if you travel far enough in any of the three fundamental directions, you loop back to where you began. It's a cosmos with built-in shortcuts, a finite container that feels infinite from the inside because you can never find a wall or an edge. This isn't just a fun mathematical exercise. A multiply-connected topology like this could elegantly solve the horizon problem, one of the key puzzles that inflation was invented to fix. The horizon problem asks why regions of the universe on opposite sides of the sky have the same temperature and properties, even though there hasn't been enough time since the Big Bang for light or heat to travel between them and establish equilibrium. Inflation solves this by saying these regions were once close together before being violently ripped apart. But a finite, wrapped universe offers a different solution. Those distant regions aren't actually distant strangers. They are the same patch of space, seen from different angles because the light has wrapped around the universe. They are in thermal equilibrium because they were always connected. We just couldn't see the connection. It's a solution that doesn't require a mysterious inflationary field. It just requires a different shape. And we can push this even further into the realm of the truly extraordinary. Consider the mind-bending properties of a Klein bottle, a shape that has no true interior or exterior. A three-dimensional version of this non-orientable topology would create a universe where concepts like left-handed and right-handed are not fixed properties but depend on your path through space. A traveler could embark on a long journey and return to their starting point as their own mirror image. These exotic shapes challenge our most fundamental intuitions about reality, suggesting a cosmos that is less a static stage and more a dynamic, interconnected manifold where the rules of geometry themselves play an active role in the physics we observe. By daring to venture beyond the comfortable, flat paradigm, we aren't just swapping one model for another. We are opening our minds to a universe of possibilities that are stranger, more wondrous, and potentially far more elegant than we have ever dared to imagine. Inflation theory has been the bedrock of modern cosmology for decades, the elegant solution that swept away some of the universe's most perplexing initial condition problems. It proposes that a fraction of a second after the Big Bang, a mysterious energy field, dubbed the inflaton field, caused the cosmos to expand faster than the speed of light, ballooning from a subatomic speck to something vastly larger in an almost unimaginably short time. This violent stretching did more than just make the universe big, it ironed it out. It took any primordial wrinkles, any unevenness, and stretched them across such vast distances that the universe we can observe appears incredibly smooth and, crucially, geometrically flat. It's a powerful, compelling story that explains so much of what we see, turning the universe's apparent flatness from a bizarre coincidence into a natural, predicted outcome of physics. But this elegant solution comes with its own set of profound and lingering questions. What, for instance, was this inflaton field? What triggered this incredible burst of expansion? And just as importantly, what made it stop? We have no direct evidence for the existence of this field. Its presence is inferred solely from its proposed effects. This places inflation in a precarious position. It's a theory that explains the evidence beautifully, but it rests on a foundation of pure speculation. It's like a detective solving a crime by inventing a perfectly motivated but entirely hypothetical suspect. The case makes sense, but the key element remains unseen and untested. This inherent uncertainty is why a growing number of physicists are daring to ask a once heretical question. What if inflation is wrong? Or perhaps more intriguingly, what if it happened, but not in the clean, uniform way we've always assumed? Consider the possibility that inflation didn't end everywhere at once or in the same way. The theory itself allows for a phenomenon called eternal inflation, where the inflationary process stops in some regions of spacetime, creating bubble universes like pockets of air in a vast loaf of cosmic bread, but continues unabated in others. In this staggering multiverse scenario, our entire observable universe is just one bubble among an infinite froth of others, each with its own random set of physical constants and laws. And crucially, each bubble could have its own local geometry. Our bubble might appear flat, but the greater multiverse beyond our horizon could be a chaotic mosaic of curves, folds, and impossible shapes. Inflation, in this view, didn't lock in a single shape for the entire cosmos. It generated a fractal infinity of them. Our flat universe isn't the rule. It's just a single, random roll of the dice in a casino with an infinite number of tables. Even if we dismiss the multiverse, a less than perfect inflation could have left its own telltale scars on the cosmos. What if the process was slightly uneven, like an imperfectly blown glass bubble? This could have imprinted a very slight but global curvature on the universe, a curvature so subtle that our current instruments, calibrated for a perfect flatness, simply can't detect it. We might be like someone trying to measure the curvature of the Earth with a spirit level designed for a tabletop. Our tools aren't sensitive enough to register the gentle, overarching bend. The anomalies we see in the CMB, the Hubble Tension, the bizarre large-scale structures, these could all be the faint echoes of an inflationary period that didn't quite finish the job, leaving behind a complex, warped geometry that we are only now beginning to sense. This isn't just academic navel-gazing. It strikes at the very heart of the scientific method. Inflation was proposed to solve problems within a specific model of the universe. But if that model itself is flawed or incomplete, then the solution might be solving a problem that doesn't exist in the way we think it does. By unquestioningly accepting inflation's explanation for flatness, we might have inadvertently closed the door on other, more exotic possibilities for the universe's shape. We may have used a powerful idea to plaster over the cracks in our understanding, instead of investigating what those cracks were trying to tell us. Revisiting inflation isn't an attack on science, it is science. It is the necessary, rigorous process of questioning our most cherished assumptions, especially when they seem to explain too much too neatly. The true shape of the universe may not be a simple, settled fact waiting to be confirmed, but a dynamic and evolving story, one that is still being written in the subtle language of ancient light and the gravitational whispers of unseen structures. But to truly grasp how bizarre our universe's shape might be, we have to venture into one of the most radical ideas in all of physics: the possibility that our reality is not limited to the 3 dimensions of space and one of time that we experience every day. String theory, a leading candidate for a theory of everything, proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. And for the math of this theory to work, it demands a cosmos with far more dimensions than we can see, often 10, 11, or even 26. Where are these extra dimensions? The theory suggests they are compactified or curled up into an unimaginably tiny space, far smaller than any particle we could ever hope to detect. To understand this, think of a garden hose. From a distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto its surface, you'd discover it has a second dimension, curled into a small circle all the way around. Our universe might be like that hose. On the grand scales we inhabit, we only perceive the 3 expansive dimensions, completely oblivious to the 6 or 7 extra ones curled up at every single point in space, a hidden microgeometry woven into the very fabric of reality. This isn't just an abstract mathematical curiosity. It could be the key to solving the very geometric mysteries we've been exploring. These hidden dimensions could be warping the apparent shape of our familiar three-dimensional world in profound ways. Imagine our four-dimensional spacetime as a vast flat membrane, or brain, floating within a higher dimensional volume called the bulk. From our perspective, trapped on this brain, the universe appears perfectly flat. All the particles that make up our bodies and our telescopes are stuck to this membrane, like ants living on a giant, floating leaf. They can scurry around in every direction on the leaf, but they have no concept of the deep pond the leaf is floating in. In this scenario, which is central to certain string theory models, the geometry we measure is just the geometry of our brain. The overall, higher dimensional shape of the bulk could be wildly curved, finite, or even multiply connected, and we would be utterly blind to it. Our entire cosmic map, built from observing galaxies and the CMB, is just a flat projection of a far richer, multidimensional reality. This perspective doesn't just add a layer of complexity. It has the power to completely redefine some of cosmology's most intractable problems. Take gravity, for instance. In our standard model, gravity is the weakest of the four fundamental forces by a staggering margin. But in the brain world scenario, gravity might be just as strong as the other forces. Its apparent weakness in our universe could be because it is the only force not confined to our brain. While electromagnetism and the nuclear forces are stuck here with us, gravity could be leaking out, dissipating its strength into the extra dimensions of the bulk. This would mean that what we perceive as the fundamental strength of gravity is an illusion, a dilution effect caused by the hidden geometry of higher dimensional space. Furthermore, what we've been calling dark energy, the mysterious force accelerating the expansion of the universe, could be a gravitational effect from a neighboring brain in the bulk, gently pushing against our own and creating the illusion of a new form of energy. We wouldn't need to invent a mysterious substance to explain cosmic acceleration. We would simply need to recognize that our universe is not alone, and that its shape is intimately connected to other realities in a higher dimensional arena. By embracing the possibility of higher dimensions, we are forced to accept that our senses and our instruments have been giving us a profoundly limited view of the cosmos. The flat universe we think we inhabit might be a local phenomenon, a mere slice of a much grander, multidimensional structure whose true geometry is beyond our current ability to comprehend directly. It suggests a cosmos that is far richer, more interconnected, and more astonishing than the flat, four-dimensional spacetime we've taken for granted. The quest to understand the universe's shape then becomes not just about mapping the curves in our familiar dimensions, but about learning to perceive the hidden dimensions themselves, and in doing so, uncovering a reality that is truly everything, everywhere, all at once. Yet for all the mind-bending possibilities of higher dimensions, an even more radical idea suggests that the problem isn't just that we can't see the full shape of the cosmos, it's that the very concept of a smooth, continuous shape might be an illusion altogether. This is where our quest takes its most profound turn into the realm of quantum gravity. Our two most successful theories of physics, general relativity, which describes the cosmos on its largest scales, and quantum mechanics, which governs the behavior of the smallest particles, are fundamentally at odds with one another. General relativity paints a picture of a smooth, curving spacetime, a stage upon which the cosmic drama unfolds. Quantum mechanics, on the other hand, reveals a subatomic world that is fuzzy, probabilistic, and fundamentally grainy. For decades, physicists have struggled to unite these two pictures into a single, coherent theory of quantum gravity, and the solutions they've proposed don't just tweak our understanding of the universe's shape, they shatter it completely. Theories like loop quantum gravity and causal dynamical triangulation propose that spacetime itself is not smooth and continuous, as Einstein described, but is instead made of discrete, indivisible units. Think of it this way: if you look at a digital photograph on your screen from a distance, it appears as a smooth, continuous image. But if you zoom in far enough, you eventually see the individual pixels that make up the whole picture. According to these quantum gravity theories, the fabric of the cosmos operates on a similar principle. At the tiniest possible scale, known as the Planck length, spacetime is not a fluid fabric but a seething, chaotic foam of these fundamental spacetime pixels. In this view, the smooth geometry of general relativity, the gentle curves around planets, and the vast, flat expanse of the universe is not fundamental. It is an emergent property, a kind of average that only becomes apparent when you zoom out from the frantic quantum jittering at the smallest scales. The universe's shape isn't a fixed classical thing. It's more like a statistical probability, a best-fit curve drawn through a cloud of quantum uncertainty. This has staggering implications for our cosmic cartography. If spacetime is foamy and discrete at its heart, then the large-scale geometry we measure, the apparent flatness, the subtle curvature, is just an approximation. It's like trying to measure the exact shape of a sandy beach. From a distance, the dunes appear to have smooth, graceful curves, but up close, you see that the surface is actually made of countless individual grains of sand, each shifting and moving. The overall shape is real and measurable, but it is not the fundamental reality. In the same way, the universe's global geometry might be stable and seemingly smooth, but underpinning it is a quantum foundation that is constantly fluctuating. These quantum fluctuations could create tiny, random wrinkles and twists in the geometry of space itself, a faint, frothy texture to reality that is ordinarily invisible to us. This perspective turns the entire endeavor of mapping the cosmos on its head. We are used to thinking of geometry as something fixed and absolute, a set of coordinates that we can chart with certainty. But if quantum gravity is correct, then the universe's form is not something to be mapped in the traditional sense. It is something to be understood through probability and interaction. The act of measurement itself, a cornerstone of classical physics, becomes part of a participatory dance with a probabilistic reality. We cannot say the universe is flat with absolute certainty. We can only say that, based on our observations, it is extremely likely to appear flat, much in the same way we can say a flipped coin is extremely likely to land heads or tails roughly half the time over many flips. The geometry becomes a statistical outcome, not an immutable truth. Bridging the colossal gap between the quantum world and the cosmic realm is the greatest challenge in modern physics, but it is also our greatest opportunity. By developing a true theory of quantum gravity, we might finally understand how the frothy, probabilistic micro-world gives birth to the seemingly smooth, classical macro-world we inhabit. This wouldn't just solve a technical problem in theoretical physics. It would revolutionize our understanding of what shape even means. We might discover that the universe's form is fluid, evolving, and deeply interconnected with the matter and energy within it in ways we are only beginning to glimpse. The quest to find the universe's shape then becomes less about drawing a final map and more about learning to speak the complex, probabilistic language of reality itself. Measuring the geometry of the cosmos is perhaps the most ambitious cartography project ever conceived, a task that requires us to triangulate the shape of reality itself using light that has been traveling for billions of years. The primary tool for this endeavor is the cosmic microwave background, that fossilized echo of the Big Bang. Missions like the Planck satellite have mapped its subtle temperature variations with breathtaking precision, and the patterns we see strongly favor a flat universe. But this conclusion isn't as straightforward as it seems. Interpreting this ancient light is an exercise in peeling back layers of interference. Our galaxy is filled with interstellar dust and gas that emit their own microwaves, creating a foreground fog that must be meticulously modeled and subtracted from the data. If our models of this foreground are even slightly off, we could be left with a cleaned signal that still contains ghostly imprints of our own galaxy, misinterpreted as a feature of the primordial universe. It's like trying to hear a whisper in a crowded, noisy room. We have to carefully filter out all the other conversations to isolate the one voice we want to hear, and there's always a risk we've filtered out something important or added an artifact of the process itself. The challenge deepens when we consider the sheer scale of the measurement. To detect curvature, we are effectively trying to measure the angles of a triangle so enormous its sides are made of the largest possible structures in the cosmos. In a perfectly flat universe, the angles of such a triangle should add up to exactly 180 degrees, just as they did in Euclid's geometry class. A positively curved universe would make them add up to more than 180 degrees, while a negative curvature would make them add up to less. But to see this deviation, the triangle has to be truly cosmic in scale. The problem is that the universe is expanding, and this expansion stretches the very light waves we use to make these measurements, potentially warping our perception of distance and angle. Furthermore, the gravitational influence of dark matter and dark energy bends the paths of these light rays through the phenomenon of gravitational lensing, adding another layer of distortion that our models must attempt to untangle. We are therefore not measuring a static shape, but a dynamic, evolving geometry using tools that are themselves being bent and stretched by the very forces we are trying to map. This leads to perhaps the most humbling limitation, the horizon of observation. We can only see so far because light has had only 13.8 billion years to travel. Everything beyond that distance is fundamentally inaccessible to us. The light from those regions hasn't had time to reach us yet. Our entire map of the universe's geometry is based on the observable volume within this cosmic horizon. If the universe is indeed infinite and flat, this isn't a problem. But if it has a more complex, finite topology, if it's shaped like a giant donut, for instance, we might be seeing the same region of space multiple times from different directions because the light has wrapped around the universe. We could be meticulously mapping what we think are distant, unique galaxies, only to be creating a flawed map because we've charted the same landmark twice, mistaking it for two separate places. Our entire cosmic survey could be biased by this repetition, a hall of mirrors effect on a scale we can barely comprehend. All of these observational challenges converge on a single, profound point. Cosmology is a science of indirect inference. We are like detectives trying to reconstruct a crime scene from a single, faded photograph taken from a strange angle. We have a wealth of data, but it is messy, incomplete, and open to interpretation. The flatness we measure is the result that best fits our current models and data, but it is not a direct, unquestionable observation. It is a conclusion we arrive at after a long and complex chain of assumptions and calculations. If any link in that chain is weaker than we think, if our understanding of foregrounds, gravitational lensing, or the fundamental nature of distance is flawed, then our conclusion about the shape of everything could be fundamentally wrong. The universe might be gently curved, but our current instruments might simply lack the sensitivity to detect a curvature so slight that it only becomes apparent on scales larger than our observable horizon. We are, in a very real sense, trying to measure the curvature of the Earth while standing in a small, foggy valley, unable to see the overarching horizon that would reveal the true shape of our world. This inherent uncertainty isn't a failure of science. It is its engine, constantly driving us to build better telescopes, devise sharper models, and remain open to the possibility that the next great discovery will be the one that overturns our most cherished cosmic certainties. For nearly a century, dark matter and dark energy have been the cosmic ghosts in the machine, the invisible hands we've invoked to explain why the universe behaves the way it does. Dark matter provides the extra gravitational glue to hold spinning galaxies together and sculpt the vast cosmic web. Dark energy is the mysterious repulsive force pushing the universe apart at an ever-increasing rate. Together, they form the backbone of our standard model of cosmology, yet we have never directly detected either one. They are placeholders, mathematical necessities that make our equations balance. But what if we've been solving the puzzle from the wrong angle? What if these phantoms aren't real substances at all, but are instead the profound and elegant consequences of us misreading the shape of the cosmos itself? This radical idea turns modern cosmology on its head. Imagine the universe does possess a slight global curvature, a gentle bend to spacetime on the largest scales that our current instruments are too crude to detect. In a cosmos with positive curvature, the geometry itself imposes a kind of tension, an intrinsic pull that could influence the dynamics of expansion. From our perspective, assuming a flat universe, this geometric effect would look exactly like a mysterious energy causing the expansion to accelerate. We would measure the universe flying apart and, lacking the correct geometric model, invent a dark energy to explain it. The force we've been desperately searching for might not be a force at all, but a simple error in our cosmic cartography, a fundamental misreading of the stage upon which the drama is playing out. The case for dark matter might be even more compelling as a geometric illusion. Our evidence for dark matter is almost entirely gravitational. We see things moving faster than they should based on the visible matter present. We see light bending around galaxies with more strength than the visible stars can account for. Our immediate conclusion is that there must be more stuff there, an unseen mass providing the extra gravity. But what if the gravity itself is being modified by the shape of space? Topological defects, think of them as permanent cosmic scars or kinks in the fabric of spacetime left over from the universe's fiery birth, could create persistent gravitational fields. A large-scale curvature, subtle but pervasive, could warp the paths of stars within galaxies and light across the void in a way that perfectly mimics the presence of immense amounts of invisible matter. We've been meticulously mapping the shadow and calling it a substance, when in reality we might just be seeing the stage itself is warped. This isn't just a minor tweak to the theory. It's a complete paradigm shift in how we view the composition of the universe. The standard model requires that 95% of the cosmos is made of unknown, exotic substances that have eluded every attempt at direct detection. If a geometric explanation is correct, it would represent a monumental simplification, a return to the beautiful principle known as Occam's razor, the idea that the simplest solution is often the best. We could potentially explain the cosmos with only the matter we can see and the forces we know, all within a geometric framework that is more complex in its shape but far simpler in its ingredients. We would be replacing two profound mysteries with a single, elegant solution. The universe isn't missing most of its content, we've just been misreading its form. Of course, this idea faces significant challenges and is far from the mainstream view. the evidence for dark matter's gravitational influence is overwhelming and observed in a huge variety of contexts, from the rotation of individual galaxies to the bending of light in massive galaxy clusters. A geometric alternative would have to account for all of these diverse phenomena with a single, coherent description of spacetime's shape, a tall order for any theory. Yet, the persistent failure to directly detect dark matter particles, despite decades of searching, keeps the door open for such alternatives. It forces us to ask whether we are chasing phantoms of our own creation, inventing ever more complex particles to explain effects that might have a breathtakingly simple, if deeply hidden, geometric origin. The true nature of the cosmos might not be found in a new particle accelerator, but in a deeper understanding of the ancient, hidden geometry written into the fabric of space and time. But what if the vast, seemingly infinite cosmos we observe is actually finite? Not finite with an edge like a box, but finite like the surface of a globe, a contained space where you can travel forever without ever hitting a wall. This is the breathtaking possibility offered by the field of cosmic topology, which moves beyond simple curvature to ask an even deeper question about the universe's connectivity. Topology is the branch of mathematics concerned with properties that remain unchanged when an object is stretched, twisted, or deformed, so long as it isn't torn. A coffee mug and a donut are, topologically speaking, the same object because one can be smoothly morphed into the other. They both have one whole. This concept, when applied to the entire universe, opens a door to realities that are far stranger than a simple sphere or saddle. In a simply connected universe, like the surface of a perfect sphere, any loop you draw can be continuously shrunk down to a single point. There are no handles, no holes, no shortcuts, but in a multiply-connected universe, space is woven into a more complex shape, like a torus, the surface of a donut, or the shape of a video game world that wraps around on itself. In such a cosmos, if you could point a powerful telescope in one direction and peer across billions of light years, you might not be looking into an endless void. Instead, you might be looking at the back of your own head. The light from our own Milky Way galaxy could, in theory, have traveled the long way around the entire universe and returned to us from the opposite direction. We wouldn't recognize it as our own galaxy, of course. We'd see it as a faint, distant, and seemingly separate galaxy, a ghostly doppelganger from a past epoch of the universe. This means the overwhelming vastness of space, with its countless galaxies stretching to the horizon, could be a magnificent illusion. Instead of an infinite expanse, we might be living in a finite, yet unbounded, volume that repeats itself. The cosmos would function like a cosmic kaleidoscope or a hall of mirrors, but on the grandest possible scale. What we perceive as unique, distant objects could be multiple images of the same finite set of galaxies, seen from different angles and at different times in their history. This would fundamentally revolutionize our sense of scale and our place in the cosmos. The universe would become smaller, more intimate, and profoundly interconnected in a way that challenges our every intuition. The hunt for evidence of this mind-bending topology is already underway. Cosmologists are scouring the most detailed maps of the cosmic microwave background, searching for telltale signs of a wrapped universe. One method involves looking for matching circles. If the universe is multiply-connected, the ancient light of the Big Bang should have taken multiple paths to reach us, creating pairs of circular patterns in the CMB with identical temperature variations. It would be like finding two identical fingerprints on opposite sides of the sky. Similarly, astronomers conducting massive galaxy surveys are looking for repeated patterns in the large-scale distribution of galaxy clusters, searching for the same geometric arrangements appearing at vastly different distances. Finding such a repetition would be like recognizing the same mountain range drawn on two different parts of a map, revealing that the map is actually of a globe and we're seeing the same feature from two different viewpoints. While conclusive evidence remains elusive, the very search forces us to confront a beautiful and humbling possibility that the true architecture of reality is a masterpiece of hidden connections waiting for us to learn how to see it. So if the universe is indeed multiply connected, one of the most elegant and surprisingly plausible shapes it could take is that of a torus, a cosmic donut. Imagine not just the surface but the entire volume of space curved in on itself in this way. In a three-dimensional toroidal universe, if you could board a starship and embark on a journey in what you believe is a perfectly straight line, you wouldn't voyage endlessly into an unknown void. Instead, after traveling an incomprehensibly vast distance, you would eventually find yourself returning to your point of departure, albeit from the exact opposite direction. It's the ultimate round-trip ticket, a closed-loop cosmos where every straight line is ultimately a circle. This geometry offers a stunning solution to one of cosmology's oldest philosophical dilemmas, the choice between a finite universe and one without boundaries. A torus is both. It contains a finite amount of space. You could, in theory, calculate its total volume, yet it possesses no edges, no walls, no terrifying precipice beyond which there is nothing. There is no outside to this universe. This elegantly sidesteps the perplexing question of what lies beyond the edge of a finite universe, or what an infinite universe even means. The torus gives us a cosmos that is self-contained, whole, and complete unto itself, a perfectly packaged reality. The local experience of living inside this cosmic donut would be completely ordinary. The curvature across the space of our solar system or even our galaxy would be so minuscule as to be undetectable. The rules of Euclidean geometry you learned in school would work perfectly for building a house or plotting a course to Mars. It's only when you zoom out to the very largest scales, on par with the size of the universe itself, that the rules change. The angles of a truly cosmic triangle would no longer add up to 180 degrees. The behavior of parallel laser beams shot across the void would reveal the subtle, overarching curvature. We are like ants living on a giant balloon, convinced the world is flat because our tiny patch of it appears to be. This hidden topology could be the key to unlocking some of the strange patterns we see in the cosmic microwave background. The mysterious cold spot or odd asymmetries could be explained if the light from a massive cosmic structure has wrapped around the universe and intersected with itself, creating a sort of ghostly echo or a double image in the sky. Our telescopes would be seeing the same patch of space twice from two different historical eras and interpreting it as two separate anomalies. Finding such matching circles or repeated patterns in the CMB is one of the active hunts in cosmology, a direct test for this breathtaking possibility. Navigating such a universe would require a star chart of unimaginable complexity. The same star or galaxy could appear in multiple places in the sky, its light having taken different routes through the curved geometry to reach us. One image would show the object as it was billions of years ago, while another, longer path might show it at an even earlier time. Astronomers would have to become cosmic detectives, determining which celestial objects are truly unique and which are merely phantoms, light echoes of a closer object seen from the long way around the universe. This would turn our map of the heavens into a complex web of connections and identities. On a deeper level, a toroidal universe challenges our most fundamental notions of isolation and uniqueness. The sense that we are alone on a tiny rock in an endless, unknowable void would be replaced by the realization that our cosmos is a closed system, a finite ensemble where everything is ultimately connected. The atoms that make up your body might, in some unfathomably distant future, complete a full circuit of the universe and return to the very spot they began. It's a shape that suggests not an alienating infinity, but a cosmic unity, a universe that is, in the most profound geometric sense, one. Yet if a toroidal universe stretches our imagination, the concept of a Klein bottle topology shatters it entirely, propelling us into a realm of geometry so bizarre it challenges the very foundations of logic and perception. To grasp a Klein bottle, first picture a Möbius strip, a simple band of paper with a single twist, creating a surface with only one side and one edge. A Klein bottle takes this mind-bending property and extrudes it into a higher dimension. It's a theoretical shape that cannot be truly constructed in our three-dimensional space without the bottle intersecting itself. It requires a fourth spatial dimension to exist perfectly. In its ideal form, a Klein bottle has no distinct interior or exterior. Its surface is continuous and unbroken, meaning if you were a tiny creature living on it, you could slide from what seems like the outside to the inside without ever crossing a boundary. It is a closed, one-sided surface, a paradox made manifest in geometry. Now, extrapolate this concept from a two-dimensional surface to the full three-dimensional volume of space itself. A universe with a Klein bottle topology wouldn't just be finite and connected like a torus. It would be fundamentally non-orientable. This is a technical term with a staggering implication. The concepts of left and right, clockwise and counterclockwise, are not fixed properties in such a cosmos. Imagine an astronaut embarking on a grand voyage across the universe, traveling in what they believe is a perfectly straight line. After an epic journey spanning the cosmos, they return to their starting point. But upon arrival, they find a profound and unsettling change. Their spacecraft's instrumentation, their own body, even the molecules that make them up, all have been mirrored. Their heart now beats on the right side. The spiraling DNA in their cells has reversed its chirality. They have returned to their point of origin, but as their own mirror image. In a Klein bottle universe, a full circumnavigation doesn't just bring you home. It flips your very handedness, challenging the most fundamental symmetries we assume are laws of nature. This property could have seismic implications for the laws of physics themselves. Many of the fundamental forces and particles in our universe are sensitive to parity, the difference between left and right. The weak nuclear force, for instance, famously violates parity symmetry. It behaves differently in a left-handed system versus a right-handed one. In a Klein bottle cosmos, this wouldn't be a fixed law but a relative one, dependent on your path through the universe. The consistency of physical laws, a cornerstone of science known as the principle of uniformity, would take on a bizarre new character. The laws would still be consistent, but your experience of them would depend on your cosmic travel history. It suggests a reality where the very constants we rely on might be, in a sense, local and path-dependent, rather than absolute and universal. While this idea remains highly speculative, firmly in the realm of mathematical cosmology, its value is incalculable. It serves as the ultimate reminder that our intuition, forged in a tiny, local pocket of a potentially infinite cosmos, is a poor guide to the universe's true nature. By daring to contemplate shapes as outrageous as a Klein bottle, we are not engaging in mere fantasy. We are stress-testing the limits of our theories and expanding the horizon of what we are willing to consider possible. These exotic topologies are the vanguard of theoretical thought, pushing us to ask not just what is the universe, but what could it be? They liberate our thinking from the comfortable confines of spheres and saddles and even donuts, forcing us to confront a cosmos that might be far stranger, more complex, and more wonderfully paradoxical than our simplest models have ever allowed. But if the universe's geometry isn't the simple, flat stage we've assumed, then the entire story of the Big Bang, that singular, explosive moment of creation, might be due for a rewrite. The shape of the cosmos is not just a feature of its present form, it is a direct relic of its initial conditions, a frozen echo of the very first moments. A flat universe strongly implies a specific inflationary beginning, a violent stretching that smoothed everything out. But if the data is hinting at a universe with curvature, then the Genesis event we've taken for granted could have unfolded in a radically different way. A positively curved, closed universe, for instance, naturally lends itself to a cyclical model. In this breathtaking scenario, the Big Bang was not the absolute beginning of time and space, but merely the latest turning point in an eternal cosmic cycle. Think of it as a cosmic lung breathing in and out across eons. A previous universe, perhaps similar to our own, would have expanded to a maximum size before the pull of gravity overcame it, triggering a catastrophic collapse, a big crunch. But instead of simply ending in a singularity, the immense energies and densities of that collapse could have rebounded, birthing our new expanding universe in a fiery big bounce. Our entire cosmos, with all its galaxies and stars, would be just one chapter in an infinite, oscillating saga of birth, death, and rebirth. The Big Bang wasn't a beginning from nothing, it was a transformation from something that came before. On the flip side, an open universe with negative curvature suggests a far more chaotic and spontaneous origin story. In this eternally expanding, saddle-shaped cosmos, the initial conditions might have been dominated by powerful quantum fluctuations. Rather than a clean, uniform explosion, the beginning could have been a turbulent, frothing sea of spacetime itself, with regions popping into existence with different properties. In such a model, our observable universe might be just one relatively smooth bubble in a vast, chaotic multiverse foam, a lucky pocket where the fluctuations were just right for galaxies to form. The geometry of openness points toward a genesis that is less a definitive event and more a random, probabilistic outcome, where the very concepts of a before and an after might lose all meaning. This isn't just academic speculation, it strikes at the heart of how we define the beginning. Our entire understanding of the Big Bang is built upon a framework that assumes a specific, flat geometry. If that foundation is wrong, then our extrapolation back to time zero is built on sand. We may have confidently traced the cosmic movie back to its first frame, only to discover we've been projecting it onto the wrong-shaped screen the entire time, misreading the plot completely. The true initial conditions could be hidden from view, encoded in a curvature so subtle that our current instruments perceive it as flatness. Unlocking the universe's true shape is therefore the key to unlocking its true origin story. It forces us to confront questions we thought were settled. Was there a singular beginning? Could time itself be cyclical? Is our universe just one episode in a far grander, eternal narrative? The geometry of the cosmos is the ultimate historical document, and we are only now learning how to read its first and most important page. This intimate link between the shape of space and the nature of time is one of the most profound revelations of Einstein's general relativity, where the two are woven together into a single, dynamic fabric called spacetime. We often think of time as a universal constant, a steady, relentless tick of a cosmic clock that everyone everywhere experiences the same way. But this is an illusion of our everyday perception. In reality, the flow of time is malleable. It's a local phenomenon dictated entirely by the geometry of the space you're in and your motion through it. Gravity, which is the curvature of spacetime, doesn't just bend the paths of planets and light, it bends time itself. The stronger the gravity, the more time slows down, a phenomenon known as time dilation, precisely measured by the GPS satellites that guide our daily navigation. But this is just the local effect. When we zoom out to the grandest possible scale and consider the global geometry of the entire cosmos, the implications for time become truly staggering, transforming it from a simple arrow into a potential labyrinth. The ultimate fate of time is inextricably tied to the shape of the universe. In a closed, spherical cosmos, time itself would be finite and could very well be cyclical. Just as space curves back on itself in this model, so too might time. The catastrophic big crunch that ends this universe wouldn't be a finale of nothingness, but a transition. In such a model, the end of time in one cycle could be the beginning of time in the next. Time would be a great circle, an eternal return where the universe is born, lives, dies, and is reborn again in an infinite loop. There is no true beginning and no ultimate end, just an endless breathing cycle of creation and destruction. This vision offers a strange comfort, a cosmic symmetry where death is always followed by rebirth. Conversely, an open, saddle-shaped universe condemns time to a very different fate. Here, the expansion never stops, accelerating into an eternal, ever-thinning emptiness. A heat death where all energy is evenly distributed and all activity ceases. In this cold, dark future, time doesn't end in a dramatic collapse. It simply loses all meaning. With no processes left to measure, no change to define a before and after, the concept of time itself would fade into irrelevance, an infinite, featureless duration with no events to mark its passage. But the possibilities become even more bizarre when we consider more complex topologies. Certain theoretical geometries, like a rapidly rotating universe or one with specific types of cosmic strings, could theoretically permit closed time-like curves. These are paths through spacetime that loop back on themselves, allowing an object, or in theory, a person, to travel into their own past. This isn't just a staple of science fiction. It's a rigorous, albeit highly speculative, prediction within the framework of general relativity. In a universe with such a structure, causality, the fundamental principle that cause must always precede effect, completely breaks down. You could potentially encounter your younger self or even prevent your own birth, creating paradoxes that defy all logic. The existence of such time loops would force us to radically redefine our understanding of free will, destiny, and the very nature of reality. Perhaps the universe would somehow prevent these paradoxes through some yet unknown law, or perhaps our linear perception of cause and effect is just a quaint limitation of our local experience within a far more complex and interconnected cosmic web. Exploring these ideas forces us to confront questions that have long been the domain of philosophers. If time is cyclical, does that mean our lives are destined to repeat themselves exactly in every cycle, or is each iteration new and unique? Does the concept of free will hold any weight in a universe where the future might ultimately determine the past just as much as the past determines the future? The geometry of the universe isn't just a dry mathematical concept. It is the canvas upon which the story of reality is painted, and that story includes the very nature of existence, consciousness, and our place within this grand, possibly infinite tapestry. By daring to reimagine the shape of all that is, we aren't just changing a map, we are challenging the most fundamental aspects of our experience, turning time from a steady, predictable river into a vast, mysterious ocean with currents and tides we are only beginning to fathom. This idea of a multiverse completely reframes the entire mystery of our universe's geometry. Instead of being a perplexing, one-off anomaly, our seemingly perfect flatness could be the most mundane form of cosmic selection bias. Imagine an infinite, eternal cosmic landscape where the process of inflation doesn't just happen once. but is constantly spawning new universes, each one a separate bubble inflating within a greater, higher dimensional meta-universe. In this staggering scenario, the physical constants and fundamental properties of each new bubble are set randomly. Some universes might form with gravity 1 billion times stronger, instantly collapsing into black holes. Others might have no strong nuclear force, preventing atoms from ever forming. And crucially for us, each of these universes would be born with its own random geometry. Some might be tightly curled into microscopic knots. Others might be wildly open saddles expanding into nothingness. And a very, very select few would have that exquisitely precise flatness or near flatness that allows for the long, slow dance of galaxy formation, star birth, and ultimately, the evolution. Life, this is the anthropic principle in its most profound form. We are not asking why our universe is flat. We are observing that we can only exist in a universe that is flat enough to allow our existence. If our cosmos were significantly curved, one way or the other, the story would have ended before it even began. A strongly positive curvature would have caused a premature big crunch, snuffing out any potential for life in a fiery instant. A strongly negative curvature would have driven matter apart so violently that galaxies and stars could never have coalesced from the primordial haze. We find ourselves in a universe that appears finely tuned for life, not because of some divine architect, but because we are the inevitable observers in one of the rare pockets where the random dice roll of physics allowed for complex structures to form. Our flat universe isn't special, it's just habitable. This perspective transforms a potential discovery of curvature from a problem into a revelation. If future observations were to conclusively show that our universe has a slight but definite positive or negative curvature, it wouldn't just break the lambda CDM model, it could be our first tangible piece of evidence for the multiverse. A universe that is almost flat but not perfectly so might be far more common in the multiversal landscape than a perfectly flat one. Our particular slight curvature would simply be the local flavor of geometry in our specific bubble, a random outcome that was just good enough to allow us to be here wondering about it. Finding that tiny deviation from perfect flatness would be like finding a single unique grain of sand on a beach and realizing it tells you the entire beach must exist. This multiversal view also unleashes the full, breathtaking potential of cosmic geometry. Beyond the simple flat, closed, and open models, the library of possible universes could contain shapes beyond our most extravagant mathematical fantasies. There could be universes with complex, knotted topologies that change over time, or realms where the number of extended dimensions is different. A universe with 4 spatial dimensions where gravity follows an inverse cube law, making planetary orbits unstable. There might be cosmos with non-orientable topologies like a higher dimensional Klein bottle, where a full journey reverses more than just handedness. The possibilities are as limitless as the multiverse itself. Our quest to understand our own universe's shape then becomes a form of cosmic archaeology. By carefully measuring the subtle curves and connections in our local spacetime, we are reading the unique signature of our bubble's birth, and in doing so, catching a fleeting glimpse of the infinitely vaster, more fantastic meta-reality that we will likely never directly see. Yet for all our sophisticated theories and awe-inspiring telescopes, we are ultimately like deep-sea explorers trying to map the entirety of the ocean's floor while confined to the surface, limited to what little light can penetrate the murky depths below. Our fundamental constraint is the cosmic horizon, a hard limit set by the finite speed of light and the age of the universe itself. We can only see the portion of the cosmos from which light has had time to reach us in the 13.8 billion years since the Big Bang. Everything beyond that is a permanent mystery, a vast and unknown volume of space from which no signal, no photon, no information of any kind has yet arrived. This means our entire map of the universe's geometry is based on a single, fossilized snapshot of a finite sphere within an unknowably larger whole. If the universe is indeed curved or has a complex topology, the telltale signs of that shape might exist on scales larger than this observable bubble, forever hidden from our view. We are trying to diagnose the shape of an entire continent by meticulously studying a single, solitary beach. This limitation is compounded by the sheer technological challenge of interpreting the faint whispers from the edge of space. Our premier window into the early universe is the cosmic microwave background, that faint afterglow from the dawn of time. Missions like Planck have mapped its subtle temperature variations with astonishing precision, but this data is incredibly noisy. The CMB signal is buried under a cacophony of foreground interference, emissions from our own galaxy's dust, synchrotron radiation, and the faint hum of countless distant galaxies. Peeling back these layers to reveal the pristine primordial signal is an exercise in statistical inference and complex modeling. If our models for these foregrounds are even slightly incorrect, we could be left with a cleaned map that still contains artifacts, ghosts in the machine that we might misinterpret as evidence for curvature or exotic topology. It's the ultimate needle in a haystack search, where we're not entirely sure what the needle looks like and the haystack is the entire sky. Furthermore, the type of curvature we might be looking for could be incredibly subtle. Imagine trying to measure the curvature of the Earth, but you're only allowed to survey a single, perfectly flat-looking football field. Your instruments, no matter how precise, would tell you the ground is flat. Only by measuring over kilometers would the gentle curve of the planet become apparent. Our observable universe might be that football field. The curvature could be so gentle, so vast, that its arc only becomes detectable over distances that exceed our cosmic horizon. Our most powerful instruments, calibrated for a flat universe, might simply lack the sensitivity and the baseline to detect a bend that exists on a grander scale than we can possibly see. We are, in a very real sense, trapped inside our own sample size, unable to step back far enough to see the true shape of the thing we are trying to measure. This is where the next generation of technology offers a beacon of hope. The James Webb Space Telescope, while not designed specifically for cosmology, is providing unprecedented views of the very first galaxies, allowing us to test our models of cosmic evolution with new rigor. Even more promising are the dedicated missions on the drawing board, like the proposed Light-Bird satellite or the ground-based Simons Observatory. These next-generation CMB experiments promise to map the polarization of the ancient light with a sensitivity orders of magnitude greater than Planck. Polarization carries a unique imprint of primordial gravitational waves, the ripples in spacetime from the universe's violent birth, which could hold the key to distinguishing between different inflationary models and, by extension, different geometric origins. They will also be far better equipped to search for the faint, telltale patterns of a multiply-connected universe, like matching circles in the CMB that would signal a finite, wrapped cosmos. But the challenge isn't just observational, it's also deeply theoretical and computational. Our ability to interpret the data from these magnificent new machines is limited by the power of our simulations and the creativity of our mathematics. We use supercomputers to run massive n-body simulations, modeling the evolution of billions of particles under the force of gravity to see what kinds of universes they produce. But these simulations are built on our current understanding of physics, which itself might be incomplete. If the universe's true geometry requires a new kind of math to describe it, a topology we haven't conceived of, or a curvature that operates in higher dimensions, then our simulations would never produce it. We might be like ancient mathematicians trying to calculate planetary orbits using only Euclidean geometry, unaware that the elliptical paths of the planets require a completely different conceptual framework. The universe's shape might not be something we can simply measure. It might be something we have to invent the intellectual tools to even see. Acknowledging these profound limitations is not an admission of defeat. It is the very essence of the scientific spirit. It is a statement of humility, recognizing that our current best picture of the cosmos, for all its explanatory power, is almost certainly a rough sketch, a work in progress. The history of cosmology is a history of such humbling revolutions, where each new generation of tools has revealed a universe stranger and more wonderful than the last. The great hope is that as we push our instruments to their absolute limits and then push beyond them, we will finally gather the data that forces a revolution, not just a minor adjustment to the density parameter omega, but a fundamental rewriting of the rules of cosmic architecture, revealing a universe whose true form is waiting just beyond the edge of our current perception, ready to astonish us all. Yet this journey into the geometry of the cosmos forces us to confront questions that have haunted philosophers and theologians for millennia, questions that strike at the very heart of what it means to exist. If the universe is not an endless, flat expanse but a finite, connected, or wildly exotic shape, it doesn't just change our scientific equations, it fundamentally alters our perception of reality and our search for meaning within it. A finite universe, for instance, would be a profound departure from the infinite void we often imagine. Finitude implies a kind of cosmic intimacy, a closed system where every particle, every star, and every conscious being is fundamentally and inescapably interconnected. In such a cosmos, the atoms that once forged a distant star could eventually find their way into your own body, having traveled a circuit of the universe over billions of years. This isn't just poetry, it's a potential geometric reality. The feeling of isolation that comes from gazing into a seemingly infinite night sky would be replaced by the humbling realization that we are all part of a single, finite, and incredibly precious whole. Our sense of individuality and uniqueness would be tempered by the knowledge that the universe might, in its grand design, be repetitive. If space is multiply-connected, there could be other Earths out there, not just similar planets, but literal copies of our world with copies of ourselves, playing out variations of our lives in distant folds of the cosmos. This challenges our deepest intuitions about self, destiny, and free will, suggesting that our story might not be a singular novel but one page in a vast cyclical library. An exotic topology like that of a Klein bottle or a higher dimensional manifold pushes these implications even further into the realm of the surreal. If the universe has no true inside or outside, or if a journey through it can reverse your very handedness, then the cosmos begins to feel less like a physical place and more like an immense, multidimensional work of art or an intricate puzzle designed by an unknowable intelligence. Understanding our place in such a universe wouldn't just be a matter of plotting coordinates on a map. It would require deciphering the underlying logic of the structure itself. The quest for meaning would become a geometric one. Are we merely inhabitants of this structure, or are we, in some way, expressions of it? If the universe is a kind of cosmic Möbius strip, a shape where boundaries dissolve and opposites connect, it could suggest that the deepest truths of existence are not found in separation and division, but in unity and paradox. This perspective resonates with ancient philosophical and spiritual traditions that have long spoken of the interconnectedness of all things, the illusion of duality, and the universe as a conscious, self-referential creation. Modern cosmology, by venturing into these exotic geometries, might be providing a mathematical language for these ancient intuitions, not proving them true, but offering a new framework through which to explore them. This shift from a cold, infinite void to a structured, possibly finite, and intelligible cosmos also reshapes the age-old question of purpose. In an infinite, flat universe, the question, "Why are we here?" can feel dauntingly arbitrary, with humanity appearing as a fleeting, insignificant speck in an endless, impersonal emptiness. But a universe with a specific, discoverable shape suggests a cosmos with defined properties and rules, a universe that is, in a sense, something rather than everything. This doesn't automatically imply a creator or a designer, but it does imply a context. Our existence emerges from and within that specific context. The purpose of a single thread is incomprehensible when looking at a tangled heap of yarn, but it becomes clear when you see the magnificent tapestry it helps to weave. Similarly, understanding the universe's geometric tapestry could be the key to understanding our role within it. We are not just passive observers of the cosmos, we are the means by which the universe understands its own shape. Our mathematics, our physics, and our relentless curiosity are the tools the cosmos has developed to comprehend its own architecture. This turns the human journey from a random accident into a potentially integral part of a cosmic process of self-discovery, lending a profound new weight to our scientific endeavors and our perpetual search for meaning in the stars. Long before telescopes and equations, humanity looked to the heavens and saw not just points of light, but grand, sweeping narratives etched in geometry. The Norse people envisioned the cosmos as Yggdrasil, a colossal, sacred ash tree whose roots and branches connected 9 distinct worlds, from the realm of the gods in its highest boughs to the land of the dead deep beneath its roots. This wasn't merely a fanciful story. It was a profound topological map of existence, a model of a layered, interconnected universe where travel between realms was possible. On the other side of the globe, many indigenous Australian cultures speak of the Dreamtime, a sacred era when ancestral beings roamed a flat, featureless land, shaping its rivers, mountains, and deserts through their journeys. The landscape itself is curved and molded by these stories, and the night sky above is a vast, domed canvas where these same ancestors reside as constellations, watching over the land they created. In this cosmology, the earth and sky are not separate realms but 2 intimately connected parts of a single, curved, and storied whole. These ancient systems reveal a universal human impulse to make sense of the vast unknown by giving it a shape we can comprehend. The Babylonians saw a flat earth floating in a cosmic ocean, sheltered by a solid, rotating dome pierced with holes for the stars. Medieval European scholars, influenced by both scripture and Aristotelian philosophy, placed the Earth at the center of a series of perfect, crystalline spheres that carried the moon, sun, planets, and fixed stars in their rotations. Each of these models was a masterpiece of its time, a coherent framework that explained observable phenomena, provided a sense of order, and situated humanity within a meaningful cosmic structure. They were built not with satellites, but with intuition, observation, and a deep need to find our place in the grand scheme of things. The geometry they proposed, whether domes, trees, or spheres, was a language for expressing relationships between the human, the terrestrial, and the divine. It is profoundly humbling to realize that our own cutting-edge scientific models are, in a crucial sense, the latest iteration of this ancient tradition. The lambda-CDM model, with its flat, expanding spacetime, is our culture's dominant cosmic story. It is supported by immense amounts of data and mathematical rigor, tools the ancients did not possess. Yet, it is still a story, a narrative constructed by human minds to explain the evidence before us. It is shaped by our cultural values, a deep belief in mathematical beauty, a preference for uniform and universal laws, and a technological optimism that drives us to build ever better instruments. Just as the medieval model reflected a hierarchical, Earth-centered worldview, our flat universe model reflects a modern, mathematical one. This isn't to say it's wrong, but rather to acknowledge that it is a product of its time, built with the tools and within the philosophical framework of early 21st century science. This historical perspective should grant us a healthy dose of intellectual humility. The flat universe is our Yggdrasil, our crystalline sphere. It is the best story we have for now, but history suggests that all cosmic stories are eventually superseded. The models of the past were not foolish or naive. They were the best interpretations of the world based on the available evidence and cultural context. Our models, for all their power, are likely just as provisional. The anomalies we're finding in the CMB, the Hubble Tension, the bizarre large-scale structures, these could be the early whispers of a paradigm shift, the first hints that our flat geometric story is incomplete. We might be like the ancient astronomers who, upon discovering slight imperfections in the motions of the planets, had to add complex epicycles to preserve their Earth-centered model, unaware that a complete Copernican revolution was waiting in the wings. Ultimately, this journey through cultural and historical perspectives reveals that the quest to understand the shape of the cosmos is a fundamental part of the human experience. It is a timeless endeavor that blends our capacity for wonder with our drive for knowledge. From the shaman gazing at the star-dusted branches of a world tree to the physicist analyzing the polarization of the cosmic microwave background, we are all engaged in the same project, drawing a map of reality. The tools change, the precision increases, but the essential mystery and the profound desire to solve it remain constant. Recognizing this deep continuity invites us to see our current scientific pursuit not as a final answer, but as the most recent, vibrant chapter in an epic, species-spanning story of curiosity, creativity, and the endless search for our true coordinates in the universe. But what if the dream of interstellar travel isn't just about building faster engines, but about uncovering a cosmic shortcut hidden in the very geometry of space itself? This is where the universe's shape transforms from an abstract curiosity into a practical roadmap for our future. If the cosmos is multiply-connected, if it has a topology like a torus or even more complex forms, it might be threaded with natural wormholes or contain regions where spacetime folds back on itself. These wouldn't be the fiery portals of science fiction, but stable features of the cosmic landscape, tunnels through the hyperdimensional bulk of reality that could connect wildly distant points in our observable universe. A journey to a star system 1,000 light-years away might not require a millennium of travel. It could be a matter of finding the cosmic backdoor, the hidden entrance that leads directly to its doorstep. Suddenly, the overwhelming vastness that isolates star systems becomes a navigable network, a cosmic subway system written into the fabric of reality, waiting for us to learn how to read its map. Even without such fantastical shortcuts, a precise understanding of cosmic geometry is the absolute bedrock of any future in space. Consider the simple act of navigating between planets in our own solar system. We calculate trajectories using the equations of general relativity, which describe how the sun's mass curves the spacetime around it. The path a spacecraft follows isn't a straight line in a flat void. It's a geodesic, the equivalent of a straight line drawn on the curved surface of a sphere. Our current models work well enough for trips to Mars or Jupiter, but as we venture farther to the Kuiper belt and beyond toward interstellar space, the cumulative effect of even minuscule errors in our geometric model could cause a probe to miss its target by millions of kilometers. It would be like trying to sail from New York to London using a map that assumes the Earth is flat. You might eventually get there, but the journey would be inefficient and dangerously imprecise. For missions that will last decades and travel incomprehensible distances, we need a perfect chart of the gravitational landscape, a complete understanding of how every star, nebula, and patch of dark matter subtly warps the spacetime through which we are traveling. This precision is already critical right here on Earth. The global positioning system in your phone or car is a daily testament to the practical power of understanding spacetime geometry. GPS satellites don't just broadcast their location, they constantly transmit the exact time according to their ultra-precise atomic clocks. Your device receives these time signals from multiple satellites and triangulates your position. But here's the catch: according to general relativity, time itself runs at different rates depending on gravity and velocity. The satellites, orbiting in a weaker gravitational field and moving at high speed relative to the Earth's surface, experience time slightly faster than clocks on the ground. If the GPS software didn't account for this relativistic time dilation, a direct consequence of spacetime's geometry, the entire system would become useless, accumulating errors of several kilometers within a single day. Your map app would guide you into a lake. This isn't a theoretical concern, it's a daily engineering correction. Now imagine scaling this up. A future interplanetary internet linking bases on Mars, outposts on the moons of Jupiter, and cities on Earth would require a synchronized clock system of unimaginable precision, one that accounts for the vastly different gravitational environments and relative speeds of each node. A flawed model of spacetime would scramble this network into incoherence, severing the lifeline of communication for future civilizations. Ultimately, the endeavor to map the universe's shape is the most profound form of exploration prep. We are like ancient Polynesian voyagers, first learning to read the stars, currents, and wave patterns before setting out across the open ocean. They didn't just build canoes, they built a deep, predictive understanding of their environment, which is what made their incredible journeys possible. For humanity to truly become an interstellar species, we must do the same on a cosmic scale. We must move beyond seeing the universe as a static, empty container and learn to see it as a dynamic, geometric entity with contours, folds, and perhaps even tunnels. The difference between a flat, infinite universe and a finite, multiply-connected one is the difference between setting sail on an endless, shoreless sea and discovering that the ocean has archipelagos and undiscovered passages that can take us to new worlds in a fraction of the time. Unlocking this cosmic cartography isn't just an academic exercise. It is the master key that could one day open the entire galaxy to humanity, turning the science fiction dream of starflight into a tangible, geometric reality. One of the most persistent ideas out there is that the universe must be infinite. It's a concept that feels intuitive because whenever we look up, the stars just keep going. But this confuses the observable universe with the entire universe. What we can see is limited by the distance light has had time to travel since the Big Bang, a sphere about 93 billion light-years across. Everything beyond that is a permanent mystery. Its light hasn't reached us yet and never will due to the accelerating expansion of space. So when cosmologists talk about the universe's shape, they're not making a claim about the entire, possibly infinite, cosmos. They are carefully analyzing the geometry of the portion we can actually observe, using the light that has finally reached us after a 13.8 billion-year journey. This measurable volume could be a tiny part of a much larger, possibly infinite whole, but its local geometry is something we can actually calculate. This leads to another crucial clarification. The shape we're discussing isn't about objects in the universe like planets or galaxies. It's about the stage itself, the very fabric of spacetime. Think of it like this: you can measure the curvature of the Earth without needing to know where every mountain and ocean is. The mountains are on the Earth, they aren't the Earth itself. Similarly, galaxies and stars are contents within spacetime. The geometry we're trying to measure is the underlying framework that dictates how those contents move and how light travels between them. It's the invisible grid that everything is painted on, and we deduce its properties by watching how the paint moves and bends over colossal distances. And if that grid is curved, you wouldn't feel it in your everyday life. This is a huge point of confusion. Many people imagine that if the universe were curved like a sphere, they'd be able to see or feel the bend, perhaps see spaceships disappearing over a cosmic horizon. But the curvature, if it exists, is incredibly subtle across local distances. The reason is scale. The Earth is curved, but when you stand in a flat, open field, it looks and feels perfectly flat because your field of view is so small compared to the planet's vast size. Now magnify that difference by a trillion times. The potential curvature of the universe would be so gentle, so vast, that it would only become apparent when measuring the angles between objects billions of light years apart. Your backyard, your city, even our entire galaxy would feel perfectly flat. The bizarre effects like traveling in a straight line and returning to your start would only manifest on a scale far, far larger than anything we can ever directly experience. This is where the important distinction between geometry and topology comes into play, a difference that is often completely lost in popular discussions. Geometry is about curvature. Is space flat like a tabletop, positively curved like a sphere, or negatively curved like a saddle? Topology, on the other hand, is about connectivity, how space is connected to itself. A classic example is a sheet of paper versus a paper cylinder. They both have flat, zero curvature geometry, but their topology is different. The flat sheet is simply connected, while the cylinder is multiply connected. If you travel in one direction on a cylinder, you loop back to your start. This means a universe could be geometrically flat, yet have a finite, toroidal, doughnut-shaped topology. Conversely, a universe could be geometrically curved like a sphere and also be simply connected. Conflating these two concepts is like confusing the material of a towel, its geometry, with whether it's laid out flat or twisted into a loop, its topology. Understanding this separation is key to grasping the truly exotic possibilities, like a finite universe without any boundaries whatsoever. Clearing up these misconceptions is far more than academic nitpicking. It's essential for understanding what's truly at stake in modern cosmology. If someone believes the universe is already proven to be infinite, they might dismiss new evidence of its finitude as impossible. If they think curvature would be something they could see out their window, they'll reject the entire concept as silly. By untangling these common errors, we open the door to a much richer and more accurate conversation about the cosmos. We prepare ourselves for the genuine possibility that the universe's true architecture is something far more wondrous and complex than our everyday intuition could ever suggest. An elegant structure whose secrets are revealed not through our immediate senses, but through the patient, collective genius of mathematics and observation. So the hunt is on, a global scientific endeavor to move beyond theory and find the hard, observational evidence that will finally reveal the universe's true geometry. This isn't about armchair philosophy. It's a meticulous, multi-pronged detective operation using the most powerful tools humanity has ever built. One of the most promising lines of investigation is a deep, forensic re-examination of the cosmic microwave background, searching for the ghostly fingerprints of a finite universe. If the cosmos is multiply connected, shaped like a torus, for example, then the ancient light from the Big Bang could have taken multiple paths to reach us. Imagine the surface of our finite universe is like the surface of the Earth. To find your way around, you can use a map that is a flat sheet, but that flat map is a distorted projection of a curved reality. In the same way, the pattern of hot and cold spots in the CMB might be a flat projection of a curved, wrapped universe. Scientists are using sophisticated algorithms to scour the Planck satellite's incredibly detailed CMB map, searching for specific signatures of this wrapping. They are looking for matching circles, pairs of rings on opposite sides of the sky where the pattern of temperature variations is statistically identical. Finding such a pair would be like discovering that two distant mountain ranges on a map are actually the same range, just seen from different angles, proving that the map is of a globe. It would be direct, incontrovertible evidence that our universe is finite, and that if you could travel far enough, you would eventually return to your starting point. But the CMB isn't the only place to look for these geometric clues. Astronomers are also turning their telescopes to the vast, three-dimensional distribution of galaxies, creating the largest maps of the cosmos ever attempted. Projects like the Dark Energy Spectroscopic Instrument, or DESI, are meticulously measuring the precise distances to tens of millions of galaxies, charting the cosmic web in unprecedented detail. In a perfectly flat, infinite universe, this large-scale structure should be random and statistically uniform on the largest scales. But if there is a global curvature or a complex topology, it would leave a subtle imprint on this galactic architecture. Certain sizes of galaxy clusters might be preferred, or vast, organized patterns might emerge that would be statistically impossible in an infinite, flat space. It would be like studying the waves on the surface of an ocean. The size and spacing of the waves can tell you about the depth and shape of the ocean floor below, even though you can't see it directly. By analyzing these immense cosmic maps, researchers are essentially performing a statistical test on the geometry of the universe itself, looking for the telltale patterns that would betray a curved or multiply-connected reality. Meanwhile, high above the Earth, a new generation of space observatories is coming online with the explicit goal of testing our fundamental cosmological assumptions. The European Space Agency's Euclid spacecraft is a masterpiece of engineering designed to create a colossal map of the universe's dark matter distribution. It won't see dark matter directly, of course, but will chart its presence by observing how its gravity distorts the images of billions of galaxies behind it, a phenomenon called weak gravitational lensing. The precise way this lensing effect works across different distances is exquisitely sensitive to the underlying geometry of space. If the universe is flat, the lensing will follow one predictable pattern. But if space is curved even slightly, it will warp the paths of light in a different way, creating a distinct signature in Euclid's data. By measuring this with incredible precision, Euclid could either deliver the most powerful confirmation yet of a flat universe, or it could reveal a slight but definitive curvature, forcing a complete rewrite of the standard model of cosmology. It is, in essence, a billion-dollar experiment to measure the angles of a triangle whose sides are billions of light years long. On the theoretical front, the work is just as intense. Physicists are not just waiting for data, they are building new mathematical models to explain what that data might show. Some are developing alternatives to cosmic inflation that could naturally produce a universe with a slight curvature or a non-trivial topology without needing a period of hyper-fast expansion. Others are exploring the deep connections between quantum entanglement, the spooky connection between particles, and the emergence of spacetime geometry itself, suggesting that the smooth space we see might be a kind of average of countless quantum connections. And at the most extreme frontier, experiments are being proposed to test the very nature of spacetime. Some involve incredibly precise atomic clocks that could, over time, detect the faint jitter of quantum spacetime foam. Others look to the next generation of gravitational wave observatories, which could detect ripples in spacetime from the very first moments after the Big Bang. These primordial gravitational waves would have been imprinted with the geometry of the universe at its birth, acting as a direct messenger from a time before time, carrying secrets about the true shape of all that exists. This vast, coordinated effort, from reanalyzing old data to building new machines and crafting new theories, proves that the question of the universe's shape is one of the most active and exciting areas in all of science. We are no longer simply assuming a flat universe. We are putting it on trial, and the jury is still out. Imagine trying to describe the taste of chocolate or the color red to someone who has never experienced them. Words would fail you. This is the challenge we face when trying to describe the shape of the cosmos with everyday language. Our intuition, built from a life spent in a tiny, local pocket of spacetime, is completely unequipped for the task. To even begin to map the universe, we need a new language, one of absolute precision and boundless imagination. That language is mathematics. It is the only tool we have that allows us to step outside our limited sensory experience and converse directly with the fundamental architecture of reality. Without it, the universe's shape would be an unknowable mystery, a secret locked in a box for which we have no key. This conversation began over 2 millennia ago with a man named Euclid in ancient Alexandria. His work, Elements, wasn't just a math textbook. It was the first rigorous attempt to define the very nature of space itself. He laid down a set of simple, seemingly self-evident axioms, like the fact that parallel lines never meet, and from them, built an entire logical system of geometry. For centuries, Euclidean geometry was considered the absolute, unquestionable truth of the physical world. It described a flat, static, and perfectly sensible space. It was the geometry of builders, of astronomers, of Newtonian physics. It felt so natural because, on the scale of our planet, it is an incredibly accurate description. But it is ultimately a local dialect, perfectly suited for describing a flat tabletop or plotting a course across a calm ocean, but utterly incapable of describing the curvature of the Earth, let alone the curvature of the cosmos. The first crack in this Euclidean certainty appeared with the discovery of non-Euclidean geometries in the 19th century. Mathematicians like Gauss, Bolyai, and Lobachevsky dared to ask a heretical question: what if we change the rules? What if parallel lines can converge or diverge? By tweaking just one of Euclid's axioms, they opened the door to entirely new worlds of geometric possibility. They discovered that space could be positively curved, like the surface of a sphere, where the angles of a triangle add up to more than 180 degrees and parallel lines eventually meet. Or it could be negatively curved like a saddle shape, where those angles add up to less and parallel lines perpetually drift apart. This was a conceptual revolution. It proved that geometry was not a single, God-given truth, but a set of consistent logical systems. The physical world could choose which one to follow. This mathematical discovery was the essential precursor to Einstein's physical theory of general relativity. Einstein didn't just use math to describe his idea that matter tells spacetime how to curve. The mathematics of non-Euclidean geometry provided the very vocabulary he needed to formulate the idea in the first place. To describe the dynamic, flexible fabric of spacetime that Einstein proposed, we need an even more powerful mathematical dialect. This is the realm of differential geometry. If Euclidean geometry is about static points and lines, differential geometry is about smooth, flowing surfaces and how they curve and twist at every single point. Its key tool is the metric tensor, which is essentially a mathematical object that tells you how to calculate the distance between any 2 points in a curved space. Think of it as the ultimate cosmic ruler, but one that can bend and flex to account for the warping of space itself. It's this mathematical framework that allows us to write down the equations for gravitational fields around black holes, model the expansion of the entire universe, and calculate how light will bend around a massive galaxy cluster. Without differential geometry, general relativity would be a beautiful but inexpressible idea. With it, we can write down the universe's shape as a set of equations and actually solve them. But geometry alone isn't enough. Geometry tells us about curvature, whether space is flat, spherical, or saddle-shaped. To understand the universe's connectivity, we need a different branch of mathematics entirely, topology. If geometry is concerned with precise measurements and angles, topology is interested in more fundamental properties. It asks questions about holes, handles, and overall connectedness. A topologist doesn't care if an object is made of rubber or glass. They only care if you can stretch, twist, or morph one shape into another without tearing it. A coffee mug and a donut are topologically identical because they both have one hole. You can theoretically smooth out the mug's handle and reshape the cup into a perfect donut. This is why topology is so crucial for cosmology. It allows us to separate the question of curvature from the question of finiteness. A universe could be geometrically flat, like an infinite plane, yet have the topology of a torus, a finite, wrapped-up space where traveling in a straight line brings you back to your start. Topology gives us the mathematical tools to conceive of these mind-bending possibilities, and even more importantly, to know what to look for in our data, like those telltale matching circles in the cosmic microwave background. The most exciting frontier lies in the development of entirely new mathematical languages. The challenges posed by quantum gravity, the attempt to unite the large-scale cosmic geometry of general relativity with the fuzzy, probabilistic world of the very small are forcing mathematicians and physicists to invent new concepts. Theories like string theory propose that the universe has 10 or 11 dimensions, with the extra ones curled up into intricate, tiny shapes called Calabi-Yau manifolds. The geometry and topology of these hidden dimensions could determine everything from the number of fundamental particles to the strength of gravity itself in our observable four-dimensional world. Other approaches, like loop quantum gravity, suggest that spacetime itself might be not smooth, but woven from a network of discrete, finite loops. This would mean that the smooth geometry we observe is an emergent property, a kind of average of a vast number of tiny quantum connections, much like the smooth surface of a pond emerges from the chaotic motion of countless water molecules. To describe this, we need new kinds of calculus and new algebraic structures that don't yet exist in our textbooks. This reveals the most profound truth about the relationship between math and the cosmos. Mathematics is not merely a tool we invent and then apply to the universe. It is a process of discovery. The universe operates according to a logical, structural pattern, and mathematics is the discipline of uncovering that pattern. The limits of our mathematics are, for the time being, the limits of our cosmos. We cannot imagine a shape for the universe that we do not first have the mathematical language to describe. Every time a mathematician develops a new concept, a new structure, a new way of thinking about space and form, they are essentially handing a new set of keys to the cosmologist. These keys might unlock doors to realities we currently consider unimaginable: a universe with fractional dimensions, a cosmos with dynamic topology that changes over time, or a reality where the very concepts of inside and outside are rendered meaningless. The journey to understand the universe's shape is therefore a partnership. The cosmos presents the puzzle, and mathematics provides the means to solve it, each new equation and theorem illuminating a little more of the magnificent hidden architecture of all that exists. Yet for all its abstract grandeur, this question of cosmic geometry reverberates with surprisingly practical and deeply human ethical implications. It's easy to dismiss the shape of the universe as a puzzle for physicists, a technical detail with no bearing on how we live our lives down here on Earth. But our conception of the cosmos has always been the ultimate backdrop against which we paint our values, our purpose, and our sense of responsibility. If that backdrop changes, the entire painting can take on a new and unexpected meaning. A finite universe, for instance, one that is multiply-connected like a cosmic donut, presents a powerful metaphor for interdependence. The realization that every particle is fundamentally linked, that the atoms in your body might one day complete a circuit of the entire cosmos and return, transforms our relationship with the universe from one of passive observation to active participation. We are not just on the Earth, we are of it, and it is of the universe in a literal, physical sense. This could foster a profound ecological and global ethics, a sense that harming any part of this closed system is ultimately an act of self-harm, that stewardship of our planet is not just a local concern but a cosmic responsibility. The fragility and isolation of spaceship Earth takes on a new poignancy when you realize the ship might be the entire finite universe, and we are all crew members on this solitary, incredible voyage. Conversely, what if the ultimate revelation is that the universe is not a coherent, ordered whole, but a chaotic, infinite, and perhaps even meaningless void? An open, saddle-shaped universe expanding forever into cold emptiness could be interpreted as the ultimate argument for nihilism. If the cosmos is destined for an eternal heat death, a fade to black from which there is no return, then any meaning or purpose must be entirely our own invention, a temporary flicker of consciousness in an ultimately indifferent void. This doesn't necessarily destroy ethics, but it fundamentally changes their foundation. Moral systems would have to be built not on a divine order or a cosmic plan, but on humanist principles of well-being, compassion, and the intrinsic value we assign to each other. The challenge becomes not finding meaning written in the stars, but bravely creating it ourselves and holding onto it fiercely, knowing it is the only light in an otherwise dark and endless expanse. The geometry of the cosmos could thus force a great philosophical reckoning, pushing us to decide whether our values are derived from the universe's structure, or whether we imbue the universe with value through our own existence and actions. This immense pursuit of knowledge itself is not without its own ethical cost. The satellites, telescopes, and supercomputers required to probe these questions represent a significant investment of financial resources, intellectual capital, and energy. In a world grappling with poverty, inequality, and a climate crisis, one must ask, is this the best use of our collective effort? The defense has always been that fundamental research, driven by pure curiosity, has a long and proven history of yielding unexpected and transformative practical benefits. The mathematics developed to describe curved space-time is essential for the GPS technology that now guides our world. The quest to understand the primordial universe pushes the limits of computing and detector technology. But beyond these practical spin-offs, there is a deeper justification, the expansion of human understanding as a good in itself. A society that stops asking the biggest questions, that ceases to look up and wonder, is a society that has begun to close in on itself. Cosmology is the ultimate expression of our species' insatiable curiosity, a project that unites humanity across cultures and borders in a shared endeavor to understand our common home. The ethical choice is not between funding cosmology or solving Earth's problems. but in building a civilization mature enough to do both, to care for its people while also nurturing the boundless curiosity that defines our humanity. Ultimately, the question of why we seek this knowledge is as important as the knowledge itself. Are we searching for comfort, for a grand design that assures us of our special place? Or are we seeking the truth, whatever that truth may be, no matter how strange, unsettling, or humbling? The ethical weight falls on scientists to communicate their findings with honesty and humility, and on the rest of us to be prepared to accept a universe that may not conform to our desires or our myths. The greatest discovery might not be a specific shape, but the dawning realization that the cosmos is far more vast, complex, and wondrous than our ancestors could ever have dreamed. This ongoing conversation between humanity and the universe is our greatest story. It challenges us to grow, to adapt, and to constantly re-evaluate our place in the grand scheme of things, ensuring that our journey of cosmic discovery is also a journey of ethical and philosophical maturation. We stand on the precipice of a new era in cosmology, a decade brimming with technological promise that could finally answer the ancient question of the universe's shape. The tools we are now building are not just incremental improvements. They are revolutionary devices designed to listen to the faintest whispers of creation and to see the subtle curves in the fabric of spacetime itself. Leading this charge are next-generation observatories like the Laser Interferometer Space Antenna, or LISA, a planned space-based gravitational wave detector. While current ground-based detectors like LIGO listen for the crashing chords of black hole mergers, LISA will be tuned to a much lower frequency, allowing it to hear the constant, faint hum of the cosmos. This hum could contain the most sought-after signal in all of cosmology: primordial gravitational waves, ripples in spacetime generated in the first frantic moments after the Big Bang. Detecting these waves would be like finding the original architectural blueprint of the universe, as their specific pattern would directly reveal the energy scale of inflation, and by extension, the fundamental geometry it imprinted on the cosmos. A clear detection would powerfully confirm our standard inflationary story of a flat universe, while a complete absence or an unexpected signal could be the first solid evidence for a radically different beginning and a completely unexpected shape. Beyond listening to spacetime, we are also building the most powerful eyes to ever gaze into the deep sky. The Vera C. Rubin Observatory, with its immense 3.2 billion pixel camera, will begin the legacy survey of space and time, repeatedly mapping the entire visible sky for a decade. This colossal project won't just catalog billions of galaxies. It will create an unprecedented three-dimensional map of the cosmic web, revealing the distribution of both visible and dark matter through the subtle distortions of gravitational lensing. The precise way that light from distant galaxies is warped on its journey to us is exquisitely sensitive to the underlying geometry of the universe. By analyzing this vast dataset with machine learning algorithms, we will perform our ultimate test for global curvature. The statistics of this lensing will either show the perfect consistency of a flat universe or reveal a slight but definitive deviation, a gentle bend in the cosmic stage that has been hiding in plain sight all along. This isn't just more data, it's data of a quality and quantity that could settle the debate once and for all. But technology is not just about bigger telescopes, it's also about smarter simulations and entirely new ways of thinking. The mind-bending complexities of exotic topologies, like a 3-torus or a Klein bottle universe, are impossible to visualize but can be modeled in the virtual realm of supercomputers. Cosmologists are now running massive numerical simulations that don't just fill a flat box with virtual particles. They run them in spaces with built-in wraparound conditions, literally simulating what a finite, multiply-connected universe would look like from the inside. They can then generate mock cosmic microwave background maps and mock galaxy distributions from these simulated universes and compare them directly to the real data we collect. This allows us to ask a direct question: does our observed universe look more like a simulation run in a flat, infinite space, or does it bear the unique signature of a wrapped-up torus? This computational approach turns abstract mathematics into testable predictions, giving us a specific checklist of what to look for if the cosmos is truly finite. Perhaps the most profound shift will come from the collision of cosmology with other cutting-edge fields, particularly quantum computing. The same quantum properties that make superposition and entanglement so strange could be harnessed to simulate the quantum state of the entire early universe. A problem that would take a classical supercomputer longer than the age of the universe to solve, like modeling the quantum fluctuations that seeded all cosmic structure, might be tractable for a sufficiently advanced quantum computer. This could provide a completely independent way to predict the expected patterns in the CMB for any given model of the universe's birth and shape, allowing for a direct, precise comparison with our observations. Furthermore, the emerging field of quantum sensing offers the potential for devices of unimaginable sensitivity, capable of detecting the faintest gravitational effects, or perhaps even probing the discrete, foamy nature of spacetime itself at the Planck scale, revealing if smooth geometry is just an illusion. This grand scientific endeavor is also opening its doors to the world through ambitious citizen science projects. Initiatives like Cosmoverse aim to harness the power of distributed computing and the pattern recognition skills of millions of volunteers. People from all walks of life could help astronomers scour the new, ultra-deep sky surveys for the telltale signs of cosmic topology, like strange repeated patterns of galaxies or anomalous large-scale structures that defy conventional explanation. By engaging the public directly in the search, we are not just crowdsourcing data analysis. We are fostering a global connection to one of humanity's most profound questions, transforming everyone into a cosmic cartographer. The coming decade, therefore, holds a spectrum of possibilities. We might finally receive the long-awaited confirmation of a perfectly flat universe, nailing down the parameters of our standard model and allowing cosmologists to focus on the remaining mysteries of dark matter and dark energy. Or we might get the most exciting result possible in science, a shocking contradiction. The data from these new instruments could reveal a slight but undeniable curvature, or even more astonishingly, a clear signature of a multiply-connected topology, proving that the universe is finite. Such a discovery would be a pivotal moment in human history, on par with the Copernican revolution or the discovery of the expanding universe. It would instantly invalidate decades of assumptions and force a complete rewrite of our cosmic story. But the most thrilling prospect of all is the one we cannot yet imagine, that our new tools will reveal something so utterly unexpected, so outside the realm of our current theories, that it will open a door to a new reality we have not even begun to dream of. No matter what we find, this relentless pursuit, driven by our innate curiosity, ensures that our understanding of the cosmos will never stand still, always evolving toward a deeper, more magnificent truth. And so our journey across the cosmos, from the domed skies of ancient myth to the quantum foam of cutting-edge theory, reaches its conclusion for now. We've seen how the question of the universe's shape is so much more than geometry. It is the very framework upon which we hang our understanding of reality. It dictates the ultimate fate of everything, influences the flow of time itself, and could even render our most profound discoveries, dark matter and dark energy, into nothing more than magnificent illusions, phantoms born from a simple misreading of the cosmic map. This isn't an abstract puzzle for physicists alone. It is a foundational inquiry into the nature of existence, one that challenges our most deeply held assumptions about where we come from and where we are ultimately headed. The current evidence, meticulously gathered by our most powerful instruments, points toward a universe that is geometrically flat. This is the prevailing wisdom, the standard model that has guided cosmology for decades. But as we've explored, this conclusion rests upon a foundation of profound mysteries, unseen dark matter, enigmatic dark energy, and a period of inflationary expansion that remains tantalizingly theoretical. The cracks in this foundation are the anomalies that refuse to go away, the Hubble tension, the cold spot in the CMB, the gravitational lensing that doesn't quite fit. These aren't mere nuisances, they are the whispers of a deeper truth, the subtle hints that our current map, for all its elegance, might be incomplete. They are the reason science must remain humble, always open to the possibility that the next observation, the next calculation, could overturn everything we think we know. This relentless curiosity is the engine of discovery. It's what drove us from a flat Earth under a celestial dome to an expanding spacetime continuum, and it is what now pushes us to consider possibilities that seem ripped from the pages of science fiction. A finite universe that wraps around like a cosmic donut, a multidimensional reality where our world is a membrane floating in a higher dimensional bulk. A quantum foam where spacetime itself loses all meaning. These ideas are not wild guesses, they are serious, mathematically rigorous explorations prompted by the data itself. They remind us that the universe is under no obligation to conform to our human intuition or our desire for simplicity. Its true nature is likely far stranger, more complex, and more breathtakingly beautiful than we have yet dared to imagine. The quest to discover the true shape of the cosmos is therefore more than a scientific endeavor. It is a fundamental part of the human story. It connects us to our ancestors who first mapped the stars and wove them into their myths, and it points toward a future where our descendants might navigate the galaxy using the gravitational currents of a curved spacetime. This search for understanding is what defines us. It is a testament to our refusal to accept ignorance, our drive to push beyond the horizon of the known, and our profound need to find our place in the grand scheme of things. So as we look up at the night sky, let's not just see a blanket of stars, but a question written in light, a question we are all a part of answering. Thank you for exploring these deep mysteries with us. If this journey has expanded your view of the cosmos, feel free to subscribe and continue the conversation.